Hello everyone, this is Vertical, a Lumbar Postural Monitor Project developed by Slendy Cabrera, Leiber Fonseca, Cristian Peña, Karen Unigarro, and my person, Natalia Perez. This is Vertical.
Musculoskeletal disorders are a relevant occupational health concern, especially in healthcare environments where workers may perform repetitive movements, patient handling, lifting, repositioning, and sustained trunk flexion. These activities can increase biomechanical stress on the lower back and other areas of the body, which may contribute to discomfort or injuries over time. In response to this problem, this project presents VertiCare, a wearable postural monitoring prototype designed to detect prolonged trunk flexion and provide a vibrotactile alert when the user maintains a potentially under-disabled posture for a defined period of time. The prototype uses an MPU 6050 inertial measurement unit to collect acceleration data, an ESP32 microcontroller to process the information and estimate the trunk inclination angle, and a coin-type vibration motor to notify the user. The system compares the measured angle with predefined angular and temporal thresholds to determine when an alert should be activated. During its development, biomedical and electronic principles such as ergonomic risk, inertial sensing, angle estimation, signal filtering, microcontroller processing, and haptic feedback were integrated. The first implementation was assembled on a breadboard to verify the sensing processing and alert stage before processing to a more compact wearable design. The experimental evaluation include repeated angular measurement between 0 and 35 grades using a cell phone measure application as a reference. In order to analyze accuracy error and repeatability, it is important to clarify that Verticare is an academic prototype and does not provide a clinical diagnosis or replace professional ergonomic assessment. Instead, it demonstrates the feasibility of using inertial sensing and vibration feedback to promote postural awareness and ergonomic monitoring.
Low back pain is pain in the lower part of the back, between the ribs and the buttocks. It can affect movement quality of life and the ability to work. In healthcare jobs, workers often need to lift, move, transfer, or reposition silence. These activities may require bending the body forward, carrying weight, and keeping in comfortable positions for a long time. Because of this, they can put extra stress on the lower back and shoulders, whose forward bending of the trunk is called lumbar flexion. This position can become more demanding when it is maintained for a long time, repeated many times, combined with lifting or performed while twisting the body. The risk does not depend only on the bending angles, it also depends how long the posture is held, or how often it's repeated, and wherever the person is handed at the back. For this project, we use 20 degrees as a reference point based on the RIBA ergonomic method. When the user bends more than this angle for a certain time, Vertical detects the posture and activates a vibration alert. The purpose is to remind the user to notice a correct and prolonged bed position. Vertical does not diagnose injury, pain, or muscle fatigue. It only measures the trunk angle as an indicator of posture. Therefore, it is an academic tool that can help improve postural awareness, but it is not to replace a doctor, physiotherapist, or a professional ergonomic evaluation.
Hello everyone, my name is Karen Unigarro and I will present the technical foundations of our project Verticare. The system uses the MPU 65 to obtain motion data and estimate trunk inclinations. These data are processed by the ESP32, which calculates and filters the angle. Then the decisions logic determines the postural conditions and, when necessary, activates the vibrations motor as active feedback. The MPU 65 is the main sensing element of our prototype. It integrates a 3-axis accelerometer and gyroscope and communicates with the ESP32 I2C. In our implementation, we use the accelerometer measurements to estimate the trunk inclination angle from the X, Y, and the Z axis. The equation so uses the tan2 function to calculate this angle according to the physical orientation of the sensor. Initially, we implemented a complementary filter with 96% gyroscope contribution and 4% accelerometer contributions. However, during testing, we observed gyroscope drift, which caused the angle to deviate from the baseline. To mitigate this problem, we changed to exponential smoothing using 0.85 for the previous angle and 0.15 for the instantaneous angle. This provided a more stable signal. For the alert logic, the motor activates when the measured angle is above 20 degrees for 5 seconds. It deactivates below 15 degrees for 500 milliseconds.
From sensor to decisions. The system follows four states. It reads the sensor, filters out the noise, decides whether there's and reads, and activates the motor. Each part uses belongs to one of these stations. Calculating the angle from this accelerometer. These lines convert the third accelerometer values into a single till angle. It's the foundation of the system. Everything else depends on these evaluates. In some calibration, on startup, the system takes 200 sample in correct postures and calculates an average. This defines each ultra-neutral posture. Noise filter. The accelerometer is inherently noise. This buffer averages the last stream, running to remove false spikes before take offensive decisions. Exponential filter. This filter blends the previous angle with the new one, giving the result stability preventing abrasions. Histories. We use the results not once. In it reads and 20 degrees and it seems 15. This kills the motor from flickering once the user is right and the battery. Activation timer. The motor only turns on if the read is sustained for 5 seconds. This light will ignore brief normal movements. Let's see the bounce. To turn off the motor will require 500 milliseconds. In correct posture, this prevents false shutdowns caused with a single noise speed key. State-based motor control. And the motor is controlled by state variables, motor ones. Update on every cycles. This guarantees continuous vibrations during reads and immediate shutdowns once currents.
This is why presents the experimental routines and the system response. During the test, we progressively incline the prototype and monitor the MPU65's measurement through the Arduino IDE serial monitor. At lower angles, the system remained in the non-risk conditions. At higher angles, the risk condition was dictated and the motor was activated. For example, at a 30-degree reference angle, the MPU65O measured 28.66 degrees and the vibration motor was activated. After verifying the functional response, we performed preliminary metrological evaluations. We use the iPhone measure application as the reference instrument. The smartphone was fixed to the prototype to maintain the same orientation during the measurements. We evaluate a reference positions from 0 to 35 degrees with 5 repeat measurements at each positions. This allowed us to evaluate accuracy, measurement error, and repeatability. Finally, we analyze accuracy and repeatability. For accuracy, we compare the mean MPU65 measurement with the reference angle. The measurements generally follow the reference trend. The maximum absolute error was 1.80 degrees at 30 degrees, while the smallest non-zero error was 0.04 degrees at 10 degrees. For precision and repeatability, we analyze the standard deviation of the pi repeat measurements. The highest standard deviation was 0.26 degrees at 30 degrees. Overall, the prototype showed generally close agreement with the reference values and good repeatability under controlled conditions, although further calibrations is required. Thank you.
Technical challenges and obstacles. We have three main problems. One, the motor when started off, isolation test so showed the wireless was fine. So the bug was in our angular logic. Second, the angle what frozen in the series because was a gyroscope dirt in our complementary filter. And three, near the 20 triggers there the motor kept flickering on and off because of sensor noise. Strategies. So, for his was thus, we fit the logic was while confirming the word's words. We're replacing in complementary filters with exponential smoothing use only the accelerometer with remove the dirt. And for the flickering with added hysteresis. 20 degrees the turn on in 15 to turn off. And place and short delay so and break moments to trade all alarms. Regulatory framework, Colombia. On the Colombia side, Resolution 2 6418. 79 covers workplace safety and mentioned vibration for equipment. 2. Decreto AUM South 172, the 2050 set up the HGAC, the National Occupational 17 frameworks. And Cancito was, with the clinical base for monitoring low back pain. Well, device regulation and international start. Decreto first 1725 and 65 regulation medical device in Colombia. Article 36 covered recent prototype like ours. International ISO 11 size 2 126 is our reference for poster thresholds. And user 14 1971 height and why so how we think about reach electrical measurement and alerted failures for features validation.
Vertical is a wearable designed to monitor lumbar, posture, and healthcare workers and help reduce ergonomic risks during work activities. The system uses an MPU system fitting inertial sensor connected to a microcontroller to measure trunk inclination in real time. In conclusion, Vertical demonstrates that low-cost technology can be used to support posture monitoring in healthcare. The integration of the MPU system fitting and provides a practical way to detect trunk inclination and generate real-time feedback. Thanks. Goodbye.